Alright, this is Hoover High, Lesson 3 Measurements for AP Chemistry. So today what we're going to talk about are measurements and the math that's associated with measurements, which is a concept called significant figures. Significant figures tells you how many digits to place in the numbers that you're measuring, how to read a measurement, and then how many digits to actually compute in your answers. So significant figures, often referred to as SigFigs, or actually sometimes even SigDig in some books or sources for significant digits, they indicate the precision of the measurement. In math terms, they provide a set of rules for how many digits you should use in your answer based on the precision of your laboratory measurements. So here's an example. Let's say we have a room and we have measured it, the width and the length, and you measure the width of the room with a laser device that's precise to 1/10,000th of a meter. The length of the room you measure with an old meter stick, and you measure it much less precisely to about 8.1 meters. So to obtain the area, you would use the formula area equals width times length, which is 8.1 times 5.2143. And that gives you 42.23583 meters, and that would be meters squared. Okay, so significant figures indicate the precision of a measurement. So this value, 42.23583 meters squared, indicates a level of precision for the measurement that's misleading because the length of the measurement could have actually been anywhere between 8.05 meters and 8.14 meters with rounding. So 8.05 would have rounded up to the 8.1 value that we used, and 8.14 meters could have rounded down to the 8.1 meter value that we used. This means that the area could have ranged between 41.975 meters squared and 42.444 meters squared. And that's a difference of about a half a meter squared. The rules of significant figures limit the number of digits you can use in the answer to 2 in this particular answer. So that means the answer would actually be 42 if shown to the appropriate number of significant figures. So now we're going to learn what these rules are and how they work. So here are the rules for significant figures. I'm just going to read them off. They won't make total sense the first time through, but then once you use them, you will see how they work. So all non-zero digits are significant, no exceptions. So anything that's not a zero is a significant figure. Zeros to the left of the leftmost non-zero digit are never significant. Zeros in between non-zero digits are always significant. Zeros to the right of the rightmost non-zero digit are significant if there's a decimal point, and not significant if there's not a decimal point. And I'll add that some books would call them uncertain, whether they're significant or not. I'll talk about that as we see some examples. So let's see some examples here. And let's see if you can determine, as we do this, how many significant figures. So how many significant figures in the number 326? The answer would be 3. All non-zero digits are significant. 3,045. Answer, 4. A zero between non-zero digits is significant, so that's 4 significant figures. 6,020. There's 3 significant figures there. No decimal, so the trailing zero, the one on the right, is not significant, or it is uncertain. Some books would say it's uncertain. Some books would say you don't count it as a significant figure. How about this number? How many significant figures? 5. Leading zeros, that's ones to the left of that 2 there, are never significant. 10,000. 1 significant figure. Trailing zeros are not significant or uncertain if there's no decimal point. How about this number? That's 8 significant figures. All zeros are significant, including the one on the far right, because there is a decimal point there. And this number, 4 significant figures. The leading zeros left of the 1 are not significant. The trailing zeros right of the 1 are significant because there is a decimal point there. Okay, now let's look at how we would do math operations with significant figures. The numbers being multiplied are called multiplicands, and the answer to a multiplication multiplication problem is called a product. So the rule for multiplication is that the product should contain the same number of significant figures as the multiplicand with the least number of significant figures. So again, let's look at some examples. Okay, so 2 times 4 equals 8. What should be the significant figure answer? Well, it's going to be 8. You have 2 multiplicands. Both of them have 1 significant figure, the 2 and the 4. Therefore, your answer has 1 significant figure. So 2 and 4 have 1 sig fig, so the answer has 1 sig fig. How about 31 times 23 equals 713? Okay, so 713 is what would show up on your calculator. What should your significant figure answer be? It should be 710. So you round that 3. Or you round the 1 using the 3, so that'll round it back down to 1 again. So it becomes 710. Each of the multiplicands has 2 significant figures, so the answer is limited to 2 significant figures. The last digit 3 should be rounded down. Okay, how about this one? What you see there is the calculator answer, 0.3432. What's the significant figure answer? 0.34. 0.104 has 3 sig fig and 3.3 has 2 sig fig, so the answer is limited to 2 sig fig. The answer is rounded down to 0.34. How about this one? How many sig fig in each of the multiplicands? Okay, so what should the answer be? 64.1. Each of the multiplicands has 3 sig fig, so the answer is limited to 3 sig fig. The 5 rounds the 0 up to a 1. And this one? 40,000. It's a little mind-blowing that your sig fig answer can be that far off from your calculator answer, but that's just simply that's the limit to the level of precision that you can show in your answer because you have a 1-digit number in your multiplicands. So the 5 limits the answer to 1 sig fig, the 2 is rounded down to 0, and all remaining digits are zeros. Okay, let's just do a few more. Sig fig answer for that? Well, it can only have 2 sig fig. So you're going to have to take that 4 and round it. And that makes the 0 that comes before it rounding back down to 0 to stay at 0. But it can only have 2 sig fig, so it's 0.00. Those are not significant. 10, those are significant. So 0.10 limits the answer to 2 sig fig. The 4 is rounded down to 0. It actually rounds the 0 down to 0, and the 1 trailing 0 are the only sig fig. This one? Well, we saw this one in our example, 42. The measurement example on the earlier slide, the 8.1 limits the answer to 2 sig fig. The 2 after the decimal is rounded down. Actually, I should say the 2 before the decimal is rounded down by the 2 after the decimal. So it keeps that 42 at 42. Okay, the rules for addition and subtraction are different than for multiplication and division. They're totally different rules. So the rules for addition, subtraction, you line up the decimals to add or subtract numbers just like you normally would to add or subtract decimal numbers. The sig fig are determined by the number with the least number of digits after the decimal. So again, let's just get to an example and you'll see what that means. So this is the way you would add these two numbers. You would line up the decimal point. And then what you do is you draw a red line, I draw a red line, and there it is. It goes next to the last digit in the number that has the least number of digits after the decimal point. So that would be 23.45. So the line goes right next to that 5. Then you add the numbers. So now what you have is 29.186. but the last digit in your significant figure is going to be that 8, so you have to round that. So the 6 rounds the 8 up to 9, and the final answer is 29.19. So you have 4 significant figures in that answer. Okay, let's do some combination problems where you have both multiplications and additions, and this could apply to divisions and subtractions as well, but we're going to stick with multiplications and additions. So the rules for combination problems are: you use the normal PEMDAS order of operations to keep track of the significant figures, but you do not round until the end of the problem. Now, practically truncating, we talked about that earlier, cutting off after the 4th place after the decimal is all right. In other words, your calculator might give you eight places after the decimal. Do you really need to write all those down? It says don't round them. Do you really need to write all those down? No. You're never going to do a measurement at that level of precision. So if you lop it off after about the 4th digit after the decimal point, you're probably okay, given the level of precision that we're going to be using in this class. And then assign the correct sig fig at the end of the problem, and then that's when you do your rounding. Okay, so let's look at some examples here. So we're going to compute 3.24 times 1.021 plus 12.1. So PEMDAS says we do the 3.24 times 1.021 first. We multiply that, and our calculator is going to give us this answer of 3.30804. Now that's going to be limited to 3 significant figures, which in this case, if this was the end of the problem, it would be it would be limited, to 3 significant figures because of the 3.24 has only 3 significant figures. So we use the rule for multiplication here, but we still don't round the 3.30804 yet. We leave it like that. Now step 2 is you add that to the final number in the problem, which is 12.1. And you see we do that the same way as we did on the previous slide. We line up the decimal points, and we draw a line next to the digit after the decimal point of the number with the least number of digits. That's 12.01. So we draw a red line right there. And then we extend it up and down. We add those up, we get 15.40804. Now that's 3 significant figures. So you're going to round the 4 using the 0. That's going to keep it at 4. So that means you're going to have 15.04. So right now, the first step gave us 3 significant figures, and the second step gave us 3 significant figures. So that is going to be the number of significant figures in our answer. Both steps 1 and 2 limit the answer to 3 sig fig. The final answer is 15.4. Let's do another one. Okay, so compute 6.02 plus 3 times 0.451. So PEMDAS says we're going to do the multiplication first. 3 times 0.451 will give you a calculator answer of 1.353, but that's going to be limited to 1 sig fig, which you don't round yet. Now we're going to add it to the 6.02, line up the decimals, draw your line, and go ahead and add. And there we have 7.373, but you're going to round that last 7. The 3 rounds it back to 7, so it's going to be 7.373. So you have 3 sig fig. The addition produces 3 sig fig, but the multiplication limits the answer to 1 sig fig. So the final answer to that is 7. So we use that final answer that we got after the addition, but we then have to look at which has the least number of significant figures, and it is the multiplication that is the limiting step there. So that means our answer in proper significant figures is going to be 7. Now with logarithms, there's a special rule. We won't get into all the math about logarithms, as I said before, but we're going to just talk about what the rule is and just kind of know it. So you count the number of significant figures in from which the log is being taken. That's called the argument. This is the number of digits that should be after the decimal in the log, called the mantissa. I know that's a completely confusing explanation, but let's just see an example and it won't be that hard. So example, the log of 12.43 equals, and you can see that big long number, that's your calculator answer. Since the number 12.43 has 4 sig fig, there will be 4 digits after the decimal place in the final answer. So that means we're going to round that long number there down to 4 places after the decimal. That would be the 094. That would be the second 4. So you're going to use that 7 to round that second 4. It's going to round it up to a 5. So your final SigFig answer is 1.0945. Don't worry, this one won't come up very much, but it's not that hard. You just have to refer back to this rule in a few weeks if you hit one of these. Okay, now let's talk about measurements, which is where we have to derive those initial numbers, the ones that we're going to put in the multiplication or in the division, or to tell us to then do the computation. So we're going to look at one of the most basic measurements, which is length or distance. So this is a standard ruler, and it has both, many times it has both metric on the top and English units on the bottom. We're going to ignore the English units. We never use those in class. Those are the inches. So that's a centimeter. And on your screen, it's pretty true to what a centimeter is, depending on the size of your computer screen. So the ruler below shows metric units on top and imperial English units on the bottom, which are inches. In chemistry, we do all measurements in metric units. The number of units on the top are centimeters. The small lines in between each centimeter are millimeters. And there are 100 centimeters and 1,000 millimeters in 1 meter. So let's take some examples. So this very first measurement, the arrow is pointing exactly at the 4. So the measure is exactly on the 4 centimeter line, so it's going to be 4.00. Now that takes a little explanation. Why 0.00? Let me read it and then I'll explain it again. Millimeters represent a precision of 0.1. So one of those 2 digits after the decimal point is the millimeter. It's the small line, because you could have 4 point some number of millimeters. We'll see that in just a minute. But in addition, this is a key point about taking measurements. In addition, the measure is allowed to estimate one more decimal place beyond what you can definitely see on the meter stick. So in other words, if your measurement is in between 2 millimeter markers, you can estimate what that is between those 2 millimeters. In this case, you're seeing that it doesn't fall in between anything. It falls exactly on the 4. So it's 4 point, and then the first digit is millimeters, and then the second digit is the estimate digit, that you think it's somewhere in between 2 millimeter measures. You can't tell for sure, or you can see for sure, but you can't tell exactly what the number is because there's no smaller markings than millimeters. But you kind of make an estimate, okay? And that is legal in science. In fact, it's the proper way to take a measurement. This allows the measurement to be 2 places after the decimal. So let's see another example. Okay, and it's hard with the resolution of your computer to really see where this arrow is, but we're going to say it's right on 6. It's right on the 7th millimeter after 6, exactly on the 7th millimeter marking after 6. So that's 6.7. However, I do get to estimate an additional decimal place, but if I think it's right on the 7, that additional decimal place will be a 0, right on the 6.7. Now, let's say on this one that we see that the measure is 2 places, 2 millimeters after the 10, but it's even a little more than 2 millimeters, but it's not quite to the 3. So it's somewhere in between the 2 and 3 millimeter marking after that 10. And let's say you believe it's exactly halfway between the 2 and the 3, then it would be 10.25. So that, again, that 5 is an estimate digit. You think it looks like it's exactly halfway, that's what you get to put down as that last digit. And finally, let's try 12.38. So you can see it's after 12 centimeters. It is after 3, but not quite to the 4. It's just before the 4th millimeter after 12. And so you estimate that that's an 8. You might have said a 9, you might have said a 7, but you estimate that's about 8 between the 3rd and the 4th millimeter marking. Then that's the guess digit that you can put in, the estimate digit you can put in. Liquids form what appears as a disc on the top, and that that glassware over there that you're seeing is called a burette. We're going to use those in class, and you're going to get a chance to use those this year. So you see that kind of funny looking little disc. And the reason why water forms that shape, this is water, the reason why it forms that shape against glass, we'll talk about. It has to do with some of the magnetic properties of water and of the glass that are in the glass. So that's called a meniscus. It looks like a little disc, or almost like a little bowl sitting on top there. So the disc is called a meniscus, and there it is. So the meniscus is the entire thickness of that little disc that you see there. The height of a liquid is always measured from the bottom of the meniscus, so you can see that right there. So the arrow's pointing to exactly where you should measure that volume. So what do you estimate that volume would be? Take a guess. What do you think that volume would be if you measure to the bottom of the meniscus? Well, it looks like it's about 3 lines down from the 21. You see the 21 up above. And it looks like it's about 3 lines down. So this 21 is in milliliters, so you could say 21.3. You may even estimate that it's a little bit below that line, possibly. And so it would be 0.31 maybe, so 21.31 might be that reading there. Now, just a side note, look at this. Something ought to seem odd to you about those numbers. They're running from the top to the bottom. So 0 is up at the top, and as they run down, they go 19, 20, 21, 22, going downward. That seems kind of odd. Don't you usually measure upward? So as you pour liquid into a container, it goes from 1, 2, 3, 4, 5 as you go up. So the lowest number's on the bottom and the highest number's on the top. For most glassware, that's true, but for a burette, you're using it to measure how much of that liquid. What it is, a burette is, it's a drip, 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 drip that's used in what's called titration. And so that means that liquid is going to be going down, 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 down. So what you do is take your initial reading before you've dripped anything out, and then you do your drip, 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 and then you see where the liquid is, you measure where the liquid is then, and then you take the difference between those two numbers. So what it means is more of the liquid is going out of the burette as you go down. So that's why the numbers start at the top and increase as you go down. That's unusual. It's different from most glassware in chemistry. Okay, so each of the small lines is a milliliter, which equals a cubic centimeter. So that's a conversion that you'll become familiar with. All right, this is a triple beam balance. You've seen this in science classes. Triple beam means 3 beams, so there's 3 of them. And as you take a look at that, the illustration below shows the beams on a triple beam balance. The center beam is in increments of 100 grams. The top beam is in increments of 10 grams. And the bottom beam is in increments of grams. The smallest lines are 1/10 of a gram, and they're called decigrams, although we seldom ever use that word. We would usually say 1/10 of a gram. That's the beam on the bottom. So I'll ask you a question in your assignment. What's the maximum number of grams that could be measured on this triple beam balance? And this is a very standard triple beam balance. So the reading on the right would be, well, what do you think it would be? Okay, so it's 500 because the largest increments are in the central beam, and you see it's at 500. And then the top beam is in increments of 10 grams. That's at 30, so that's 530. And then you can see the grams down at the bottom are between 6 and 7. So it's 536. And then you go to one of the decigrams, one of the tenths of a gram. So that would be, it looks like it's at about 8. And then remember, you get to make an estimate digit beyond that 8. But the resolution on this is not good enough to tell where that is exactly. So we'll just leave it at a 0. We'll say it's exactly 0.80. Okay, so the 0 is the estimate digit. The resolution of the image is not clear enough to tell where the point lies between 8 and 9. Okay, now we're going to look at measurements of time, and they are what they are. You know all of these. They're the same no matter what system of measure you use. So it's one thing that everybody was able to agree on. So second, minute, which are the most common ones we'll use in chemistry here, but it can also be hour, and then it can also be calendar time. A day, a week, a month, a year, a century, even beyond. When you're dealing with radioactive decay, there are some isotopes whose decay, whose half-life is the age of the Earth, and even beyond. So you can have some very long time frames on it. All right, so that takes care of our lesson on significant figures and measurement. So it all really starts with measurement. You take the measurement, but then you need to know how many figures can you read from your measurement. It can't be an unlimited number of decimal places. And then once you've determined that in the lab, how many decimal places you are going to record your measurement as, then you can do calculations following the rules of significant figures. So the two subjects go together. Okay, that's the end of lesson 3. We'll see you again on lesson 4 when we start talking about the atom.